Right, in here I'm going to talk about the momentum in 2D. This is the part 2 video. So we're going to do the problem. So we're on page 16, number 38. So it says a 60 kilogram halfback moving east at 5 meters per second. So that's a momentum of 300 kilograms meters per second is tackled by a 40 kilogram free safety heading north at 10 meters per second. So that's a momentum of 400 kilograms meters per second. What's the magnitude of the final momentum of the combination? Now, the initial momentum has to equal the final momentum as vectors, meaning the momentum is conserved in all directions. So the initial momentum, the total initial momentum, and the total final momentum will have the same magnitude and the same direction. So if I close this triangle here, what you see in green there, that's the initial momentum, and it's the final momentum. Okay, so if you do Pythagorean theorem, you should get 500 kilograms meters per second. Now to find, I can write this as prime here. Okay, so this P prime is 500. You have to show how to do that. Kilograms meters per second. That's also the mass of the combination, which is 100 times the velocity of the combination after they stuck together. So it should be 5 meters per second. And to figure out the angle, you just have to do the inverse tangent of 4 over 3 or 400 over 300 to get that angle there. All right, so the answers are on the answer key. So that angle is about 53 degrees north of east. Now let's look at number 39. A 6 kilogram body moving at 5 meters per second south collides with a 4 kilogram body moving 8 meters per second east. So I always do east and west first because the angles, when we measure the angles, we go with the east and the west. Okay, so I'm going to go with the one going east. That's a momentum of 32 kilograms meters per second. The other one is going south. That's a momentum of 30 kilograms meters per second. What is the magnitude of the initial momentum of each body? We did that. The initial momentum of the system, meaning like the combination. That's when it says the initial momentum of the system, that's basically the total momentum. So we have to find out what that is. So if you do Pythagorean theorem here, you should get that to be about 43.86 kilograms meters per second. Now I'm not going to do the math here. You should be able to do that. What is the final momentum of the combination? Well, I think first we have to get the direction here. So you can figure out this angle here by doing theta is the inverse tangent of 30 over 32. And that angle should be about 43 degrees south of east. Okay, the final velocity of the two bodies, if they stick together, well, this is also going to be the final momentum. So your final momentum is this much, and that's equal to the mass of the combination, which is 10 times the velocity of the combination v prime, and that should be 4.39 meters per second. And it's going to have the final velocity is going to have the same direction as the final or initial momentum, and the reason for that is P equals mv. So the vector P and the vector V have to have the same direction because the mass here is always positive. So and we know that if you multiply a vector by a positive scalar, it does not change its direction. Okay. All right, now we're going to do things that are not at a 90-degree angle. A 10 kilogram body moving at 4 meters per second east, so it's going to have a momentum of 40. collides with a 3 kilogram body moving at 7 meters per second at 30 degrees north of east. So we do the head to tail, and this is 21 kilograms meters per second. What is the magnitude of the initial momentum of each body? I think we can figure this out. This 40 and 21, we did that already. what is the initial momentum of the system, meaning like what's the total momentum as a vector here. So we have to figure this out. I'm going to do this with law of cosines. If you need to see how it's done with the chart, you have to go back to the answer key on Haiku and see how I did it. Okay, or you can go back to the previous video, the part 1 video. So this is the initial momentum of the combination. That's also the final momentum of the combination. Now here, we're going to do law of cosines. So I know that this angle here is 30 degrees, so which leaves me with 150 here. Okay, and once I get that, I can say, well, P initial or P final are the same, and that's equal to, using law of cosines, 40 squared plus 21 squared minus 2 times 40 times 21 cosine of 150 equals 59.13 kilograms meters per second. Now we have to figure out what this angle here is. So let's figure out what that angle theta is, right? So I think here we're going to do law of sines, but when you're doing law of sines, you have to be careful because two angles will work. So it could be the angle or its supplement. So you find the first angle that the calculator gives you, make sure that it makes sense inside this triangle. If it doesn't make sense, you have to pick the supplement of that angle. So here I'm going to do sine of theta over 21 equals sine of 150 over the initial or the final momentum, which is 59.13. And this angle here is 10.23. Okay, so I have to make sure that it makes sense, because if it doesn't make sense, I have to pick the supplement. And here you can see that the supplement won't make sense, because the supplement of that is 170, and if that's 170 and that's 150, you already passed 180. So I wouldn't even check in this case here, but sometimes you have to. Okay, so the P final equals the P initial as vectors equal 59.13 kilograms meters per second at about 10 degrees north of east. Okay. All right, let's look at number 41. A 4-kilogram ball moving east. Okay, so we don't know the momentum of it. Okay. Grazes a stationary 4-kilogram ball. The incident ball moves off at 15 meters per second at 53 north of east. The target ball moves out. Okay, so here it is. So one of the objects moves this way at 53 degrees, and it's going to have a momentum of 60. This is 4 kilograms. And the other one is going to move at 37 degrees, and it's going to have a momentum of 80. Okay. Now, what was the original speed of the incident ball? So now, since we have information about the final state, we're going to stick with the final state. But one thing we have to know is the combination of the momenta of these two here, of these two balls, has to be east. That's not negotiable, because your initial momentum is east. So the final has to also be east, and it has to be the same. Okay, so I set it up like this. So this is the 60, this is the 80, and I'm trying to figure out this final momentum, which is also the initial momentum. Now this angle here is 53. This angle here is 37. This is the alternate interior, that's 37. This is 53. I'm left with a 90 here. So this becomes easier. We don't need to do law of cosines. We can just do a Pythagorean theorem and get the initial and the final momentum. So if we do that, we should get P prime equals PO equals 100 kilograms meters per second. That's a special triangle, right? A 6, 8, 10. Okay. And then we can do the velocity of this object, of this ball here before the collision. It's just going to be, well, PO equals MV. So this is going to be 100 equals 4 times V. So V is 25 meters per second in the east direction. Okay. Okay, 42. A 20 kilogram moving object explodes. So we have an object that's moving and it breaks into pieces. A 5 kilogram piece goes off at 8 meters per second at 50 degrees north of west. So one of the pieces, the 8 kilogram, moves in this direction at an angle of 50 degrees. And it's going to have a momentum of 40. The 15 kilogram piece goes off at 4 meters per second at 20 degrees north of east. So the other one is going to go in this direction. It's going to have a momentum of 60 and a mass of 15 kilograms. What was the velocity of the original 60 kilogram object? So what I'm going to do, I'm going to try to find the momentum of the combination after the explosion, and that's going to be the momentum of the 20 kilogram ball before the explosion, and from there I can find its speed and its direction. So let's try this. This angle here is 20. So I'm going to put these two guys head to tail, and I really don't care which one you start with, so I guess I'll just start with the, I don't know, I'll start with the 60, I guess. So here's the 60. Okay, and then I'll come here and I'll put the 40, and I have no idea where it's going to extend, so maybe I'll just stop there. Okay, this is 40. Okay, and this is my resultant. Okay, so this is my initial momentum. That's also my final momentum. See, if I can figure out what this angle is here, I can do love cosines. If you want to see how it's done with the chart method, you can go back to the answer K on haiku. Okay. Now this angle here is 20 degrees. This angle here is 50, but this angle here is also 20, because these two are alternate interior, so which leaves me with a 70-degree angle here. So this whole thing is 70. So now I can say P initial is P final. I keep writing F, but it's a prime. It doesn't matter. So that's 60 square plus 40 square minus 2 times 40 times 60 cosine of 70. If you do the math correctly here, should get 59.65 kilograms meters per second. Now we have to figure out the angle. Now to figure out the angle, I need to figure out this whole angle here. Okay? And then I would subtract 20 from there to get, yeah, actually we need to figure out that whole angle. Okay? So if I can figure out the angle in green here, okay, all I have to do is add 20 to it. So I'm going to do love signs here. So sine of theta over 40 equals sine of 70 over over this red leg here, so which is 59.65, and I should get an angle of, I don't have a calculator. Okay, John, do you have a calculator? Thank you. Mr. Hughes is helping me out here. So let me try this here. So sine of 70 divided by 59.65 times 40, and we do the inverse sine of that, and the answer is 39 degrees. So this is 39, and I have to add 20, so let's just say 39 degrees. Let's say it makes sense first of all. Okay. This leg here is 59.65. This leg here. So if this is 100, this is going to be 71 degrees, I think, right? Yeah. 71. I don't think that makes sense, because you have a 70. Actually, no, I think it makes sense. Yeah, it does make sense. Yep, it does make sense. Okay, so the answer should be 59.65 at 59 degrees north of east. To find the velocity, just take this number here and divide it by 20, and the answer should be 2.98 meters per second at 59 degrees north of east. Okay. All right, let's try number 43. And as you can see, I'm doing all this with law of cosines. If you're interested in the chart, you can go back to the haiku page. A 10,000 kilogram truck moving west at 25 meters per second collides with a 7,000 van moving south. Okay. So this is a right angle collision. So the momentum of this guy here is 2, 5, and 4 zeros kilograms meters per second. The van is going to be 1, 4, and 4 zeros kilograms meters per second. If the two vehicles stick together, find the speed. So, well, this is the initial momentum. That's also going to be the final momentum. And once I figure this out, I can do P equals mv to find the speed. So I think here we just have to do Pythagorean theorem, figure out what that angle is, and that angle is going to be the same for the velocity. So I'm not going to do this one because this is kind of like similar to the other ones we did earlier. A 50 kilogram scale is traveling east at a speed of 3 meters per second, which means a momentum of 150 kilograms meters per second. A 70 kilogram scale is moving due south at a speed of 7 meters per second. So that's a momentum of 490 kilograms meters per second. They collide and hold on to each other. So they stick together. So this is the initial momentum of the two. That's also the final momentum when they stick together. All right, so here if you want to figure this out, you have to do a Pythagorean theorem here, and your answer should be 512.45. So this should be 512.45 kilograms meters per second. To find the speed, you just take that number and divide it by the combined mass, which is 120 kilograms. And to find the angle, you just have to do the inverse tangent of 490 over 150. But if you want to use 512, you can just do sine or cosine. I'll let you to do it any way you want. All right, let's look at this ranking tasks, and we're done. Okay. So RT9. I already read the problem. So which letter best represents the direction of the initial momentum of ball T? Well, T, this is the direction of travel of ball T, right? So this is the initial velocity, and this is the final velocity, right? So I guess V0T, V final T. Okay, momentum and velocity have the same direction, okay, because the mass is positive. So when the ball T is coming, it's going in direction D, okay? And I think I just said the explanation verbally just now. I'm not going to write it down. The final momentum of ball T is going to be B, okay? Which letter best represents the direction of the change in momentum of T? That's a different story. So now the final momentum of T is in this direction, okay? That's the final momentum of T. And you have to change in momentum is final momentum minus initial momentum, okay, as vectors, right? So we have to do the head to tail, but you have to take the initial momentum of the ball and flip it, because you have to subtract it and put it at the head of this vector here. So it's going to look like that. Okay, so this is the initial momentum of T, but it's the opposite of that. So this is your change in momentum of ball T. So that's going to be going in the A direction. Okay. Which letter? Okay. Which letter best represents the direction of the change in momentum of ball S? Let's take a look. The final momentum of ball S is going this way here. Okay? Now the initial momentum is going up and to the right. So if you subtract that, you're going to be going down and to the left. So this is the negative initial momentum of ball S. This is the final momentum of ball S. So if you combine this point to the last arrowhead, that's the change in momentum of ball S. Okay, so that direction would be E. Okay, which letter best represents the direction of the impulse on ball T? That should be A. That's the impulse is the same as change in momentum. And the same thing applies to question F. The impulse on ball S is exactly the same direction as the change in momentum of ball S, because we learned that impulse causes your momentum to change. So impulse equals change in momentum. All right, let's look at RT10. Okay. Identify the closest directional match for the direction of the momentum of the two-ball system before they collide. Okay. So the 2 kilogram has a momentum to the right, and the other one has a momentum to the right, up. Okay, so if you combine those, your total momentum will be right and up. So excuse me. Okay, for case B, we're going right and down. So it's going to be going to the right and down. So that's going to be, looks like it's P. For C, they come in at each other with the same momentum. So it will be no direction. So that's J. And the last one, the one coming from the right side, the 3 kilogram, has more momentum than the 2 kilograms. So the combination will be to the left. So this is S. The next question is identify the closest direction match of the direction of the momentum of the two-ball system after they collide. Well, momentum is conserved. So the direction of the momentum of the system before the collision equals the direction is the same as the direction of momentum of the system after they collide. So direction is conserved and magnitude is conserved. okay, because we are in 2D now. Okay. Identify the closest directional match for the direction of the impulse on the ball for these cases. So I think what we need to do here is figure out the change in momentum, and the change in momentum is impulse. Okay, and maybe later I can talk about it conceptually and see why the answers are going to match with what we're going to talk about conceptually. So the final momentum is to the left because it's showing you that the ball is going to the left. Okay? And it's greater than the initial momentum. So you have to do final momentum. Okay? Final momentum minus the initial momentum. Well, the initial momentum is going to the right. The opposite of that, come to the head of this and you draw the other one. So the change in momentum is to the left, which means the impulse is also to the left. That's the same. Change in momentum and impulse are the same. So this is an S. Okay. For case B, I mean, it's obvious that the impulse has to be to the right because you go into the right and then your momentum increases to the right. So the impulse has to be the right. That's what I was saying. We can do this conceptually. Going back to A, you could have said, well, the object is moving to the right, and then 5 seconds later, it starts to move left. So which means you had to stop somewhere and come back, which means it must have been a force acting on it to the left. So here you have the momentum of the ball after 5 seconds, and then you subtract the momentum of the ball before, which was less actually, okay? Because earlier it was going at 3 meters per second. So now here is your change in green. So it has to be going to the right. That's O. For part C, so the final momentum is going up, and you have to subtract the initial momentum. So the initial momentum was going to the right. The opposite of that is to the left. Okay? It's all about arrows, you know? Just follow your arrows. Okay? So this is going to be going up, up, and left. T. Okay. This one here, you're going down. You're going to do the opposite of the initial momentum, which should be to the left. So your final momentum / impulse is in the R direction. Okay. Now the next question says, identify the closest directional match for the direction of the change in momentum for the ball for this. Okay, I think we just answered that. So I think I answered the second question before the first, but basically the two questions are asking you the same thing. Okay? Yeah, so impulse and change in momentum are exactly the same thing. So I think I answered B before A. See you later, and I hope this helps. Take care.
All right, I'm out. Peace.